mention a few things. First of all, we have the ITC reception for the first time after the pandemic. Will take place in, I think, yeah, a couple of weeks on Saturday. So that will be the 23rd, I believe, of September. Everyone is invited. There was a message sent by TJ Martin. Maybe some of you did not notice it, but you're all invited. Usually, just to explain to those who are not familiar, because it was a long time ago when we had the last reception, basically we have food and people just speak with each other. That's it. No program. And it's just an opportunity for you to socialize, to meet people that you're not familiar with, especially the new ones that arrived. So it's a great opportunity for people to meet each other, socialize, and have great food. We usually have excellent food for a few hours. We will have a bus leaving the Center for Astrophysics. I think we are starting it at noon, so the bus may leave at around 11:30 or so, and the details will be provided by TJ Martin once we know how many people want to use the bus. Okay, so that we are waiting for you to say yes, I'm coming, so that we can make reservations for the right number of buses. Okay? So we all welcome you, and it will be held, hopefully the weather will be nice, it will be held outdoors. And speaking about new people, I just wanted to mention that we not only have new postdocs, but we have new faculty. Isn't that amazing? 2 new senior faculty this year, and it has been a while since we have had new faculty, really. How many years was it? 5, 7? I forgot. I didn't count. Well, it's not because of us. We always wanted the new faculty, but we were not given authority or the authorization by the dean for a long time. They claim we have enough faculty. So now we have 2 new ones, and that's we are so pleased to welcome Ashley Villar. Where is Ashley? Is that who here? No, she's not. Well, she's in the ITC corridor, so you can see her. And Catherine Zucker. Is Catherine here? Oh yeah, here she is. So both of them are in the ITC corridor, and we are delighted to have you nearby. And then we have a few new ITC postdocs. So actually the first one I would mention alphabetically is giving a presentation shortly. Scott Lucchini. Scott there? Yes. Cassie Lockhas is, I believe, not here yet, or is she? Yeah, she's coming, I think, in a week or so.
She's here, but she's traveling.
Oh, she's traveling. Okay. And by the way, she and Sarah are helping to organize a discussion. So we changed the format of the ITC colloquium. It will be a discussion. So there will be a round table where all of you are invited, as well as other people within the CFA, to discuss a topic of great interest in astrophysics, and there will be a person that guides the discussion in terms of the content, but that person will not give a talk. I'll just mention a few facts about the subject, and then all of us around the table will speak for 1-2 minutes at a time. There will not be a single person dominating the conversation. And the idea is to foster collaborations and new ideas about the subject that is unresolved. There are many such subjects, and maybe a lot of papers will be written as a result. That's the hope. And this format was suggested as a result of a town hall discussion we had with the CFA community about how to make the colloquium better, and the decision was to have this forum, so we hope to see you all, and it will be completely democratic. Everyone can speak out, and hopefully it will lead to collaborations. So that's, I was reminded of that because of Cassie, and she's helping to organize it. And then Katie Brower, NSF Fellow from MIT. Is Katie here? No. So hopefully she will be coming soon, and in a few weeks we will have a group photo outdoors. Hopefully the weather will still be accommodating. And we have obviously new astronomy grad students, 11 of them, and I wanted also to thank the luncheon organizers, Yuying Ni. Is Yuying here? Oh, she's up there. We have actually a second floor here. And Scott Lucchini is helping in that, and Evan Bauer. Evan? Traveling. And as well as obviously PJ Martin, Uma Mirani, and we have a new administrator, Jasmine. Where is she? Oh, here she is. And we are delighted to have you with us. Yeah. Because just to let everyone know, Mark Palmer moved to the astronomy department, so he's still around, but
he is.
Yeah, we remember you very fondly. Okay, so that's for announcements, and just respond to the ITC reception. So let's start with Scott Lucchini, the incoming postdoc, and he will tell us about the Magellanic corona and its role in the evolution of the Magellanic stream.
Okay, is this microphone thing working? Yeah. More or less? Great. Hi everybody, I'm Scott Lucchini. As you have heard, I'm a new ITC fellow here. Just started this week, so still getting my bearings, but excited to be here, and I'll be talking a little bit about my PhD thesis work on the simulations of the Magellanic system. Before I get to that, a quick bit of background. I did my undergrad at the University of Rochester in upstate New York. After that, I spent 3 or 4 years in software doing front-end development for a startup called Heredo. And then I went back to school and got my master's in theoretical physics at the University of Edinburgh. A year in Scotland was absolutely amazing, highly recommended. And then I did my PhD at Wisconsin, University of Wisconsin, Madison, working with Elena Hoemann on the Magellanic system. I defended in June, and we've been here for about a couple weeks now. This is my family, my wife, Amanda, our 2 daughters, Madeline, who's 3 years old, and Susie, who's 9 months old, and our dog Duke. So this is us. We're excited to be in the Boston area. I grew up in central Massachusetts, so it's coming home for me. And we'll see what the next 3 years bring. But back to science. Here we've got the Magellanic system. This is observational data from Naomi McClure-Griffith's Galactic All-Sky Survey, showing H1 21 centimeter emission colored by velocity, line of sight velocity. And so this strip here is the Milky Way disk, and this up here is the Magellanic system. The large and small Magellanic clouds are here, dwarf galaxy satellites of the Milky Way, and then intertwined turbulent filamentary stream extending upwards in this projection. This is the Magellanic stream. And on top of this neutral material that we can see in emission, this beautiful structure, absorption line spectroscopy studies have investigated the ionized material associated with the Magellanic system as well. So these dots are absorption line spectroscopy sight lines where ionized gas has been detected, again colored by velocity. And you can see that there's a whole bunch of it extending a large region on the sky, co-moving with the Magellanic clouds and the stream. So on top of the neutral material, we have this ionized gas, and it actually constitutes 78% of the total mass of the Magellanic system, bringing the total mass up above 10 to the 9 solar masses, between 1 to 2 times 10 to the 9 solar masses of gas that is approaching the Milky Way. And this was one of the big mysteries that motivated my PhD work. How can we explain this massive amount of ionized material in addition to the neutral stream that we've been looking at for decades? The second piece is the mass of the LMC. Here I have a figure showing the observed LMC mass on the x-axis for a variety of different references using different techniques to indirectly estimate the total mass of the LMC. This bottom plot point is a direct measurement of the rotation curve. So this is only the mass included within about 9 kiloparsecs, so it's not actually probing the total halo mass of the LMC, which is why it's an outlier here. All these other methods use different techniques to estimate the total mass. There's observing perturbations to stellar streams in the Milky Way halo. There's abundance matching based on the stellar mass of the LMC, and then cosmological arguments such as the timing argument or the satellite population of the LMC all seem to indicate a high mass for the LMC above 10 to the 11 solar masses, with an average about 1.5 times 10 to the 11 solar masses, about 10% of the Milky Way. And so we need models of the formation of the stream and the evolution of the cloud that can account for both of these things. And if the LMC mass is quite high, we would expect it to not just come by itself, not just come with the SMC, but also come with its own circumgalactic medium of warm ionized material around it. And so in my work, we've proposed the existence of a Magellanic corona, a warm circumgalactic medium around the LMC, that is surrounding, cocooning the interactions between the LMC and the SMC over the past couple billion years. So we have the LMC and the SMC orbiting around each other, gravitational tidal forces stripping material out of their disks and into the trailing stream that we can observe in neutral gas, all the while embedded within the Magellanic corona, which envelops the neutral material in this ionized gas that we've observed in the absorption line spectroscopy studies. And so my first task was to determine, well, if we have this circumgalactic medium, can it explain the magnitude of the ionized gas observations that we see? And the answer is yes, luckily. This is a plot showing the total mass in the trailing stream split up by neutral material in purple and ionized material in orange. The observations are on the left here. There are two previous publications, Gertina Beslow's work from 2012 and Stephen Pardy's work from 2018, that also explored this tidal model of interactions, but they weren't able to they weren't looking to explain the ionized material. However, once we include the Magellanic corona, we see a similar amount of material stripped through the tidal interactions, but on top of that, there's this ionized component originating in the LMC CGM, bringing the total mass above 10 to the 9 solar masses in agreement with the observation. So it seems like this Magellanic corona can solve this mystery of where did all of this ionized gas come from that we see around the Magellanic system. And my recent work has been looking to constrain the properties of this Magellanic corona by looking at the observations. So we've been exploring, ionization fraction in our simulations is 82% compared to the observations of 78%. So comparable values in what we're finding in our simulations. We've been exploring the parameter space of initial temperatures and total masses for the Magellanic corona to see what sort of results we can get for the Magellanic stream at the present day. To explore the temperature effects, we started with just the LMC by itself. We initialized with a Magellanic corona and no LMC gaseous disk, just a corona by itself, and the disk forms self-consistently by the material cooling and condensing and falling to the center of the gravitational potential well. And by changing the temperatures, we get very different properties of the LMC disk that forms. If we start with a cold Magellanic corona, we get a very large disk. If we start with a hot Magellanic corona, we get no disk at all because the material doesn't cool and fall to the center of the potential well. In order to determine which of these temperatures is correct, however, we need to compare with the observations. So here's our observational data. The LMC disk is this bright circle up in the top left corner. And here's our three simulations. Clearly, the medium temperature at 3 times 10 to the 5 Kelvin provides the best match to the size of the LMC's disk. In the observations, we see a bit more diffuse material surrounding than we do in the simulations, but the goal here was just to look at the disk itself. And so this seems to be the best value for the temperature of the Magellanic corona, which in fact agrees with the virial temperature calculations that we've been doing from the get-go. In varying the total mass, as you'd expect, the more mass we have in the Magellanic corona, the more ionized material we observe at the present day. And so here's a similar plot to what we saw in the previous slide. The observations are on the left. And here are three models, a low, a medium, and a high mass Magellanic corona model. And the total amount of ionized material increases in each case. We need at least 5 times 10 to the 9 solar masses in our Magellanic corona initially in order to cross that 10 to the 9 solar mass barrier that we see in the observations. But if it goes too high, up to 10 to the 10 solar masses and above, it's not stable anymore because the LMC's mass is only a little over 10 to the 11 solar masses. It's not able to hold on to all that material. So our fiducial values for the mass and the temperature of the Magellanic corona are 3 times 10 to the 5 Kelvin and 5 times 10 to the 9 solar masses. And if we perform a simulation of the LMC and the SMC interacting with each other with this Magellanic corona falling into the Milky Way, this is what we get. And this includes a lot more physics than what we've previously published, which is one of the really exciting results here. You'll notice this bottom right panel is ionization fraction. We have every individual particle in the simulation has a fraction, has its own ionization fraction that's tracked based on its temperature and its interactions with the other particles in the simulation. And so we're comparing this to our absorption line spectroscopy results that are able to calculate ionization fraction from cloudy ionization modeling, and this agrees very well. If we look at the morphology of the trailing stream here, compared with the observations in the top left-hand corner, the blue is showing the neutral 21 centimeter emission. We see discrete filaments in the trailing stream. The length of the stream agrees very well. And the overall morphology, this turbulent little bumps and wiggles, agree with the morphology that we see in the observations as well. The top right plot is showing our ionized material that we're comparing against carbon-4 observations from the absorption spectra. And it covers a large fraction of the sky, as we see in the wide spread in data points here from the carbon-4 detections. So it seems like the Magellanic corona can explain the total ionized mass in the Magellanic stream, and it also contributes to the correct morphology and properties of the trailing stream in its evolution as well. One last slide to tie this into what I'm planning to do here. I am planning to extend my study to circumgalactic media around galaxies in general, looking at specifically the multi-phase nature of the CGM and how the cold clouds and cold clumps in the circumgalactic medium fuel star formation, how they form, where they go, and things like this. So I'll be using isolated galaxy simulations combined with cosmological simulations to trace these clouds. Here's a high velocity clouds around the Milky Way compared with the neutral gas around a galaxy in the illustrious TNG simulations. And by combining these results with isolated simulations, we'll be able to improve the resolution in space and in time to really see what's going on with these multi-phase circumgalactic media. So I'm over in P245, and there's my email that finally got set up yesterday, so please come say hi. Thanks so much, everybody.
Another thing that you can use to constrain your models would be globular clusters, because in principle they are highly correlated with the halo properties of galaxies. So
Yeah.
did you try to do that? Or another way to put it is this is a pair of galaxies entering the Milky Way,
Right.
carrying about 10% of the mass of the Milky Way.
Right.
And there would have been additional components to this. It may have been a group of galaxies.
Right. Yeah, so there has been some work looking at what other galaxies could have fallen in with the Magellanic clouds, a so-called Magellanic group. And there are several contenders that seem quite likely that they've come in. And then there's somebody down at Space Telescope, I don't recall who, but they're looking at the globular clusters around the LMC to estimate its mass out to directly observe its mass out to larger radii. That will give us another line on that plot I showed at the beginning, which is very interesting.
Yes, the Milky Way is not spherical for sure.
Yes, right, and I've been talking to Jesse about that as well, looking at the triaxial nature of it and how that will affect the orbits and the infall. Really interesting.
Okay, questions? Comment? Go ahead.
Nice talk. Can you show the plot of ionized fraction and constant temperature? Yeah, this one.
This guy, yeah.
So, yeah, you show that the disk size depends on the temperature, right? But
Right.
the neutral fraction, mass of the neutral gas doesn't. Right? So it's like the same mass, but
Yeah, so in this, on the right here, these are all the same temperature using this middle value, and these are using this all the same mass using this value. So I've just been varying one thing at a time. Is that?
okay, so the mass of the disk also changes when you change the temperature.
Yeah, so the total neutral mass in the disk changes when I vary the temperature, even though the total mass of the Magellanic corona is held fixed, because more of it cools and falls to the center when you start with a cooler temperature. Yeah.
Ramesh?
Yeah, so as this Magellanic system orbits through the Milky Way halo, you would expect, of course, this diffuse gas to get stripped up, right?
Right.
So how long do you expect your corona to last?
That's a great question. So I think that it won't last more than one orbit.
Wow.
So right now, our models propose that the clouds are on their first infall. They're just approaching the Milky Way for the first time now. So they've only been passing through the Milky Way's halo for about 1 billion years. And so that's why we're able to still see some of this material here. But you can see that the ram pressure forces are pushing it all behind the LMC. It's not spherical anymore, of course. But then once it goes around one more time, it's basically all gone. And it's all then phase mixed into the Milky Way's halo.
So could you remind me, I know that I've heard stories both ways.
Right.
That the LMC is making its first pass versus it's actually been going around a few times.
Right, yes.
What is the current understanding?
So based on the velocities of the LMC and the SMC, the most recent statement has been they're coming in for the first time because the velocities are comparable to the Milky Way's escape velocity. And so they're moving too fast to have already come around once. However, there was a recent paper this spring that showed there is a possible model, an orbit, that are consistent with the velocities where they do loop around once. However, it was only n-body. There wasn't any gas dynamics. And I think because we see this widespread in ionized material, that's another indication that it's most likely these clouds are on their first infall because we still see ionized gas associated. It's not all stripped. So that's a quick summary.
So if we have further observational probes of the extent and the shape of the Magellanic current present day, could you use that to constrain the density profile of the Milky Way CGM at the outer radii?
Yes, definitely. Because the shape of this ionized material depends on the density profile and the mass of the Milky Way CGM, because it's the ram pressure forces of the Milky Way CGM on the Magellanic corona that shape this ionized gas. So if we have more information on what this looks like, we can constrain the Milky Way for sure.
Great. Let's thank Scott again.
Thank you very much.
Can everyone hear me? Great. Okay. Right. Fantastic. It's great to see everyone back in person, and very good timing that Scott just gave a talk about the Magellanic system in stream. I'm really excited to talk to you about a paper that we put out this summer, finding a stellar counterpart to the Magellanic stream. But first, I wanted to start off with just a bit of background, even though Scott already covered some of this. What you see here is the Magellanic stream. It's been known for about 5 decades. This beautiful stream of gas dominating the southern sky, emanating from the Milky Way's most dominant neighbors, the large and small Magellanic Cloud. However, for these 5 decades, we've been missing some key pieces of information about the Magellanic stream, namely its distance and how it moves on the sky. These are 2 pieces of information that stars give us, but gas doesn't. And so, as a consequence, the precise distance, kinematics, and even the origin story of the Magellanic stream has been a bit uncertain. And the explanation that people have appealed to as to why we have not yet found stars in the Magellanic stream is simply that perhaps the Magellanic stream itself is too far away. It's at 100 kiloparsecs or so, far beyond the reach of classical spectroscopic surveys that run out of stars after about 30 or so kiloparsecs. So that's been the story as to why we haven't found stars yet. And so that's where our work comes in. Since I got here 2 years ago, I can't believe it's already been 2 years, a major part of my PhD thesis has been finding and identifying the most distant stars in the Milky Way. So we've developed techniques to identify luminous red giants in the outskirts of the galaxy, peering apart from all the more nearby dwarf stars. And then for the past year with Charlie Conroy and Rohan Naidu, I've been having a lot of fun running my own mini spectroscopic survey, where we use the Magellan telescope in Chile and we go and get detailed spectroscopy of all of these stars. And so this finally gives us their distances, precise chemistry, and their 3D motions. And the survey's already done pretty well. We have more than 200 stars in the outer halo, including 50 stars beyond 100 kiloparsecs already. And just for context, that already doubles the number of red giants in the field halo with this kind of detailed information at those distances. And so we quickly realized that with this data set that we've assembled in the southern hemisphere, this is a prime place to look for stars plausibly associated with the Magellanic Stream. And the way we did that is very simple. It's undergraduate physics. We do this based on angular momentum. As Scott mentioned, the Magellanic Clouds are likely on their first infall towards the Milky Way, and as a consequence, they have this very energetic high-velocity orbit that sticks out like a sore thumb in angular momentum space compared to other stars at similar distances. And so, if we simply plot our data set of stars beyond 50 kiloparsecs in this angular momentum space, what we found is that we have stars that look like they're in the halo of the Milky Way, but there's also a very prominent tail of stars with extreme angular momenta reminiscent of the clouds themselves. And so this was pretty promising, and so we just draw a little box around those stars to pick stars that appear to be moving along with the clouds. And this is what we get. We get 13 stars in our data set, and they're plotted here on the sky in radial velocity and in distances. And the x-axis is the angular coordinate along the gaseous Magellanic Stream, which is shown in black over here. The shaded bands over here are predictions from numerical simulations that a former ITC member, Gertina Besla, ran in 2012 of what this stellar counterpart might look like given the information that we knew about the clouds and the stream at that time. And as you'll see, these stars that we observe actually do a remarkable job of reproducing those simulation-based predictions and the gas in these spaces. And so you get this kind of coincident stream population that falls out of our data set just by performing that kinematic cut. However, I hope all of you are still not fully convinced that these stars did come from the Magellanic Clouds, and if so, that's good, because there's two more pieces of evidence that we appeal to make this argument. The first one is the orbits of the stars themselves. So on our laptops, we can actually integrate these stars back in time in a model of the Milky Way that includes the large and small Magellanic Cloud. And not only do these stars go back and trace the past orbits of the clouds, but some of them actually have a high probability of becoming bound to the LMC in this simulation. And so that's very strong dynamical evidence that these stars were actually chucked out of the clouds as the clouds fell in. The second clue that we appeal to is the precise chemistry of these stars, which we get from our spectroscopic survey. So in this chemical plane of alpha abundances versus metallicity, this teaches us about whether the stars were cooked up gradually in a small galaxy or cooked up very quickly in a big galaxy. And it turns out that the stars that we observe all look, chemically speaking, like stars that we currently find in the Magellanic Clouds themselves. And so when you put all of these ingredients together, you have a population of stars that is spatially, kinematically, and chemically consistent with being the bona fide stellar counterpart to the Magellanic Stream. And the reason we finally found it is because we went looking in the outer reaches of the Milky Way. So okay, just to conclude, apart from solving astronomical mysteries, why should anyone actually care about this? I think one of the cool consequences out of this is the fact that we found the stars at these distances perhaps suggests that the gas itself goes out further than people have thought. And so, as Scott mentioned, the mass of the neutral part of the Magellanic Stream could actually be as much as 2 times what people typically assume. And this is the Milky Way's dominant breakfast, lunch, and dinner for the next couple of billion years. So this has consequences for our galaxy's future. But I think what I'm most excited about is kind of what I motivated at the start of the talk, which is we now have these new constraints, namely the distances and detailed motions of these stars that future simulations of the clouds can aim to reproduce. And so I'm really excited to see the kinds of sophisticated simulations Scott was talking about try and reproduce the stars that we've observed. And I'm really confident that'll teach us more, not only about how the Magellanic Stream formed, but also teach us more about the details and history of the Magellanic Clouds themselves. And so I wanted to close by really thanking the entire team that put this together. You can read the paper. It was accepted yesterday. And you can scan that QR code if you want. And I'm really happy to take questions.
So Vedant, how far do you expect the stream to continue? Is there a chance of finding more?
Yes, that's a really good question. So if you see here, you'll see that we've identified stars up to 100 degrees away from the clouds out to 100, 120 kiloparsecs. This is around where the neutral gas at least starts to run out. But I think there is evidence for ionized gas going a little bit further. And so I think it's totally plausible that you see more stars over here. And so actually this semester and the last semester, we're filling out this region of sky with our spectroscopic survey a little bit more. And so we might actually find a couple more stars in this region from our survey.
Can be used to constrain the tidal field from the Milky Way and therefore the halo structure.
Exactly, yeah.
Go ahead, Eric.
On your chemical plot, you had two questions. You had alpha over Fe. What's that? And secondly, why do these abundances have these complex curves in this plot?
Yeah, those are both really interesting questions. So the alpha over Fe is just the fraction of alpha elements, so things like calcium, magnesium, over iron. And as I described it, what this basically tells us is the abundances of elements that are formed in core collapse supernovae, which is sensitive to essentially the timescale over which the stars are formed. And so on plots like these, stars that are cooked up gradually in a tiny dwarf galaxy like the Magellanic Clouds tend to be on these lower down tracks. Stars that are cooked up in larger dwarf galaxies like the Gaia Sausage Enceladus merger tend to be higher up on these tracks. And then the Milky Way is even more to the top and to the right on this plot. And then in terms of the wiggles over here, the wiggles that you see on this plot are because of data, because these trends that I've shown you here are median trends that we observe in the Magellanic Clouds. But also models of chemical evolution will predict that you have wiggles. As the star formation history of the galaxy evolves and you have stars being formed on different timescales, you'll have different wiggles in this space naturally. Yeah.
Any other comments, questions?
Yeah.
Yes, please, go ahead.
Do you think that the stars formed in the stream or were tidally stripped out of the LMC?
Thank you. This was not a plant, but that's an amazing question. So we don't know. And so the one part that I kind of glossed over when I showed you these stars is there's actually two populations that we observe, right? This metal-rich population that follows the gas closely and a metal-poor population that's slightly offset. And so we discussed this in the paper. It is possible that that metal-rich population was in fact formed in the stream. It's so metal-rich that it could have also been formed in the disk of the LMC itself. The metal-poor population, however, is more mysterious because it's so metal-poor that it likely had to come from the outskirts of the clouds. And so I kind of glossed over this, but not only do these stars give us information because of where they are and how they move, but the chemistry of these stars actually teaches us about where in the clouds they could have come from. You can't have a very low metallicity star sitting in the center of the LMC disk. That's a little bit unlikely. And so that's an added bit of constraints that simulations, that we can use to constrain simulations. Not only do the stars have to match up, their birth locations in the clouds have to be plausible, given what we see. Yeah.
But isn't the density of those Magellanic streams so small that the G's mass is huge?
So the thing is that in the leading arm of the stream, there is actually a small star cluster that recently people have started arguing might have actually been formed in situ. So we haven't looked at it in too much detail, but just based on that, I think it is plausible. I think, yeah, certainly we don't expect star formation to be going on right now, but it's plausible that at some point in the past, maybe there was star formation. Yeah.
Yes.
Yes.
All the way back to the very beginning of the talk, your selection.
Yes.
I was just wondering, you mentioned parallax and IR selection, so presumably zero parallax is what you were looking for?
Exactly.
And then IR selection, I just wonder if you could just comment on how you might have changed it now in retrospect, what the precision and completeness is like.
Yeah, that's a fantastic point. So again, I glossed over this because this was kind of covered in some previous work that I worked on. Yes, this is a very important part of the puzzle. How can we execute a spectroscopic survey at Magellan with the confidence that we're going to have a high probability of finding these faraway stars? Because this is, 0.5% tip of the iceberg. 99.5% of stars with similar colors are going to be far more nearby dwarfs. And so as you mentioned, the first step we do is we ask, given the apparent magnitude and color of the star, is the parallax consistent with it being a giant, or is it a larger parallax that suggests it's a dwarf? That throws out most of the dwarfs. And then there's an IR selection that we perform that, again, because of differing, the SED is slightly dependent on the surface gravity of the star, and so that also cleans up the sample a little bit. And so the sample is incomplete. It's not complete at all because we have to perform all of these cuts, but it's highly pure. And so far in our survey, we've gotten 0 dwarfs and 1 quasar. So it's pretty pure in terms of finding giants.
Let's thank Vedant again.
And you can plug this in.
Okay. Okay, so yeah, thanks for having me. My name is Elena Hoemann. I'm a guest from Munich, and I'm finishing up my PhD thesis, which I did together with Andreas Burkhardt. And yeah, I want to talk about one of the main findings in my PhD thesis, which was about the fragmentation of interstellar filaments, which is a matter of timescales. And just to set the stage here, some introductory slides. So we start out with the diffuse interstellar medium, which condenses to thicker regions, which is shielded from the outside UV irradiation, where molecules can form. And it has been observed that these molecular clouds are infiltrated by interstellar filaments. And these filaments are known to be the hosts of star and planet formation. And here I show you some examples of such filamentary structures, which look a bit different. For example, you see here in Orion, where we have these rather complex filamentary shapes, the same in Polaris over here. In Taurus, we have a more isolated filament, and here in Aquila, you see this huge filamentary network indicated by the blue lines. And if I now show you where in Aquila the protostellar cores are situated, then you see that they exactly match the structure of the filaments. And this shows that star formation is happening inside these filaments, which has been already known for a long time. And this is what makes them so interesting for us, because if we want to understand star formation, we need to understand the physics of filaments. And the question, of course, now is, how do we get from the filaments to the stars? And in my PhD thesis, I investigated several different mechanisms which undergo filaments in their lifetime. I have some works about the merging of filaments, also about the collapse of filaments. But today, I want to focus on the fragmentation of filaments, which is mainly also depending on the involved timescale, as you will see in the following. So for me as a theorist, the filament is more like a cylinder, as you can see over here. It's defined by a certain length and a confined radius. Also an important quantity to mention is the criticality of a filament, which is the mass of a filament divided by its length, divided by the critical mass per length. So that means if F is smaller than 1, you have a radially stable configuration, but if F is bigger than 1, the filament would start to collapse in radial direction. Okay, so with that, I want to show you how a filament is supposed to collapse. So if you have a filament with a constant density distribution along its main axis as initial condition, the acceleration which you have along the filament just due to self-gravity looks a bit like this. So we have this sharp increase in acceleration at the end of the filament. And this leads to the fact that over the overall collapse of the filament, matter is piled up in the end regions of the filament. And this is the so-called edge effect. So this is the first fragmentation mechanism I want to talk about today. The second one is if we already start out with some perturbations inside the filament, they can grow over time, forming cores which are aligned along the filament. So both of these effects are governed by their specific timescale, the edge effect formation timescale and the perturbation timescale. And both of the timescales depend on different quantities. Both depend on the criticality of the filament and also on geometrical factors. For example, the edge effect formation timescale depends on the radius of the filament, the perturbation timescale on the perturbation strength, which is initiated in the first place. But the edge effect itself also depends on the acceleration which you have in the end region of the filament, which induces this edge effect. And this is exactly what you can see now over here. So on the y-axis I show you the time, and on the x-axis the acceleration, and you see that the edge effect has this strong dependency on acceleration, whereas the perturbation time scale stays constant. So if you now have a filament end region which looks like this, so at the end of the filament the density just drops to the outside density, then you would expect to have an acceleration which is more or less in this domain over here. And you see that the edge effect formation timescale is much lower than the perturbation timescale. So in that scenario, you would always expect the edge effect to be the dominant effect inside the filament. The problem now is that this effect is only rarely observed. And most of the observations show more structures like this here in torus, where you have the cores aligned along the filaments, which would hint towards a perturbed solution. So somehow we have to dampen the acceleration into this little regime over here, where perturbations actually can grow faster than the edge effect. And the idea was to insert this gradient here over here, which then can diminish the acceleration at the end region. And this is exactly what happens. So we can reduce the acceleration until perturbations can indeed grow faster. And what's now, of course, interesting in that regard is the crossing time here, where the two timescales are equal. So both effects would occur on the same timescale, because this would be then the gradient which is minimally needed for perturbations to grow faster. And we calculated this gradient, which you can see over here in this red box. And it's mainly dependent on the criticality and density, but also on the dominant perturbation growth and the perturbation strength, which is initially there in the filament. On the right-hand side, I now show you a graphic of this. So the y-axis shows the the gradient, and the criticality is given here on the x-axis. And the curve shows the critical gradient, and everything below the curve you would expect that the edge effect should be the prominent fragmentation mechanism, and everything above would be perturbation dominated. We checked that with simulations, with hydrodynamic simulations, and it worked out quite well. Although we had some deviations for filaments, for light filaments. And here I show you now numerical calculations in comparison, and you see that we have this offset over here. But this is kind of expected because we had to do some approximations to derive this equation. So you just have to keep in mind that for light filaments, you even need smoother gradients than the critical gradient to stop the edge effect. And here, for more massive filaments, the approximation of the critical gradient is in very good agreement to simulation and also to the numerical calculations. And now, the last question is, of course, whether these gradients are actually what suppresses the edge effect. So a comparison to observations would be nice in that regard. However, there are no observations available so far which have looked at the ends of the filaments. So now the question would be to see whether observations can really see the predicted gradient which are necessary or which we predict so that perturbations can grow faster inside the filament. And just my last statement, for understanding the physics of star formation, it's very helpful to look at the timescales because we can learn a lot from looking at them. And I thank you for your attention, and I will be around until tomorrow, so if you have any questions, you can come to the guest office and ask me. Thanks.
You didn't define the critical mass to length ratio, but is it, I mean, if you multiply by Newton's constant, G times m over L, that has units of velocity squared. So if that thing is bigger than the velocity dispersion squared, then it's critical. Is that the condition? So, or the sound speed squared, basically?
I mean, the gradient itself is...
No, the definition of F.
The
What is
definition.
critical ratio, and is that relative to the sound speed squared, basically?
Yeah, it's depending on the sound speed of the filament.
Yeah.
So it's the highest line mass you can achieve by having a hydrostatic equilibrium.
Right, so it's basically when gravity dominates over sound speed squared, like the G's
Yeah,
condition,
yeah,
but now
exactly.
in 1 dimension
Yeah.
instead of 3 dimension.
Yeah.
Okay. Ramesh?
So I was just wondering, how strong is the magnetic field in these filaments, and does it at all play any role in this collapse process?
That's a very good question. I mean, in the study we didn't include any filaments because we wanted to understand the basic setup first. But that would be like one of the next steps to look at whether we can slow down the process or something. But we haven't looked at that at all.
But even a simple thing, is the field along the filament or is it perpendicular to the filament?
That depends. There are several observations which have.
Both?
Yeah.
Okay.
How does the dynamic of the whole filament influence this? Because I guess if you have a filament which is moving in like stretching or compressing by itself, that would change a lot.
I mean, we consider all of these filaments to be like collapsing along the main axis because there's no hydrostatic solution for the axis along the filament.
The collapse you mentioned is only radial, am I right? Not on the length too.
The radial collapse is defined by F. So when there's like, but along the filament there's no hydrostatic solution. So you would expect every filament to be somehow collapsing. So this is already like included in the theory more or less. But of course other velocities or initial velocities we haven't looked at here because of we just have this basic study. But of course that could also influence and slow down the collapse timescales.
Lisa?
I don't want to be the observer that rains on the parade. The magnetic field's bad enough, but the problem that's worse is that a lot of these filaments are very transient and they're formed as a result of much larger scale processes that Kevin can tell you about that. And so the idea that you have a static, hydrostatically supported filament is probably almost never true at these scales. And instead you have these things that have a lot of non-thermal motion inside of them, and then you're observing them at different stages in their very short lives, and hoping that they're in this kind of hydrostatic condition. And so I'm just wondering, like, if you take a picture like this, you don't know how old this thing is, you don't know why this thing formed, you don't know what the internal motions of this thing are, and I'm just wondering when and if you might want to give up on this kind of hydrostatic
Yeah, I mean, of course, this is highly idealized. I know that, but I mean, to understand the underlying physics, I guess it's a good first start to understand the interior, because we do observe these cores which are aligned along the filament, and there are also some observations which show the edge effect itself. So somehow this approximation seems to work in some filaments and lead us to understanding of some underlying structures. But of course, the next step would be to look to the bigger picture. How does surrounding influences influence the collapse timescales, influence the creation and evolution of the filament? That would be kind of the next step.
If I was going to be constructive, what I'm saying is it would be great if you guys could take some of the filaments that are in the larger scale simulations and use those as starting conditions, and then see how much of an analytic calculation you could do using that.
Yeah, that would be super interesting to compare our isolated simulations to. Yeah.
Elena, to paraphrase what Elisa just said, because you're finishing your PhD, what makes a theorist happy? The lack of data. Because once you have a lot of data, your theory might not be so simple.
True, yeah.
Let's thank Elena.
All right, so my name is Angelo Ricarte. I'm a postdoc at the Black Hole Initiative down the street, and today I'll be telling you about new recipes for black hole jet feedback and spin evolution that I did together with Ramesh Narayan and Brandon Kurd, who you may know recently defended here. So we know that black holes are able to launch relativistic jets, and jet feedback from accreting black holes at the centers of galaxies is believed to be crucial for galaxy evolution. In the most massive halos in particular, they're responsible for making sure the gas doesn't overcool and overproduce stars. But exactly how one implements this in simulations has not been resolved, despite the fact that we've known this for many decades. In this picture on the left of the well-studied jet in M87, you can see the problem. Jets that are extending for kiloparsecs, or sometimes almost a megaparsec in length, are launched from structures that are maybe microparsecs to milliparsecs in size, depending on the mass of the black hole. And thus the field has spent decades trying to devise smart subgrid models that try and capture the salient physics while producing reasonable galaxies. I'll be talking about the very smallest scales, where we can gain insights from general relativistic magnetohydrodynamic simulations, or GRMHD, where you can evolve magnetized plasma in a Kerr space-time. And there's a particular class of these models that has been gaining popularity as of late. This is the magnetically arrested disk, or a MAD. These are models that have a saturated magnetic flux on the horizon that has been brought in by the accreting magnetized plasma, unlike their standard and normal evolution or sane counterparts, pun very much intended. And in this cartoon from Ramesh back in 2003, the idea is that the magnetic field has been brought in and has gathered up to an extent where the magnetic pressure is comparable to the gas pressure, causing transformations in the magnetic field geometry and the dynamics of the system. Nowadays, these models are favored by Event Horizon Telescope studies, produce a natural mechanism for flares, magnetic flux eruptions. Sometimes you'll see that in this movie on the right, where a big hole appears. And they actually arise from generic initial conditions on cosmologically short timescales. What's really interesting for a cosmological point of view is that they efficiently launch very powerful electromagnetic jets via spin extraction. This is called the Blandford-Znaick mechanism, or BZ. And the governing equation for these jets is shown here on the bottom left, where the jet's efficiency is proportional to the spin of the black hole as well as its normalized magnetic flux, both squared. And so you're dependent on both the spin and the magnetic field strength of the black hole. We showed in recent work that because you're actually extracting spin using these jets, that actually leads to significant spin down. There's this spin up parameter that is called S that you'll see again. It's the ratio of the rate of change of the spin versus log of the mass. And for an analytic thin disk, the prediction as a function of spin is this dashed black line. It's always positive, that's why it's a spin up parameter. But for MAD GRMHD simulations, we found in fact very large negative values that were significant enough to spin down a black hole over cosmic time. For example, if you take a black hole that starts at a spin of 0.9 and let it evolve for a gigayear at Eddington ratio of 3 times 10 to the minus 3, it'll be more like 0.5. It's kind of slow, but this could result in gradual spin down of black holes that are accreting at a low rate for a very long time, which may be relevant for maintenance mode AGN in clusters. What we were after in this project were more universal signatures, and in particular in the super Eddington regime, instead of the very low Eddington rate regime, you end up with similarly geometrically thick disks that can also confine powerful jets. In existing work, what I had been showing you before, this was only valid for very low Eddington rates, where given a spin, you can predict the efficiency of the jet and the spin-up parameter. There were completely separate formulae for thin disks worked out a very long time ago by Bardeen. And as you increase above Eddington ratio of 1, the behavior had been uncharacterized. So what we had wanted to do is rectify this and formulate a unified picture. And the way we did this was to run 38 GRR MHD simulations. These are now including radiation, which are in the mildly sub-Eddington to super Eddington regime. Here we're exploring 2 different masses and a variety of spins. And importantly, we now make the ansatz that all of these accretion flows are mad. That is, they've saturated the amount of magnetic flux on the horizon. From these, we calculated a bunch of quantities with the aim of computing jet efficiencies and spin down in particular. And there were a lot of ingredients that went into the eventual semi-analytic model that we developed, but I'll highlight this most important one, which is a link between the accretion rate and the magnetization. What you're seeing here is each point is one GRMHD simulation color-coded by the spin. And on the left, we have magnetization as a function of Eddington ratio. You can see that as the Eddington ratio increases, the magnetization increases and maybe saturates at some point. We know that there's a spin dependence. That's why there are different colors here. So this means that disks with higher accretion rates are able to confine larger magnitudes of magnetic fields on their horizons. And then given a spin and a magnetization parameter, it turns out that the Blandford-Znayak mechanism correctly predicts the energy output extremely well. That's shown here on the right, where the curves in the background are the predictions from the BZ model. And if you compare similar colors, you'll see that they do a very good job. So devising fitting functions for this, as well as other intermediate quantities, we developed a model that, at the end of the day, gives you something like this. What you're looking at now is the spin-up parameter as a function of spin, now color-coded by Eddington ratio instead of spin. On the top, we have values directly computed from the GRMHD, and then the bottom comes from this model that we had developed. The most important trend is that if you look at a fixed spin, particularly in the prograde range, as you go from a lower Eddington rate to a higher one, you move from the thin disk solution, which is this dotted line, towards something more like this dashed line, which came from MAD pure GRMHD. On the bottom, the model that we developed works very well at capturing this behavior and even smooths out a lot of this numerical variability and noise. There are a couple interesting curves. So at a fixed Eddington rate, you can map out what the spin-up parameter is as a function of spin. This blue line is Eddington ratio of 1. It's similar, but not the same as the thin disk solution. And then as the Eddington ratio goes to infinity, you get something that is very similar to pure MAD GRMHD. These are actually the first spin evolution formulae in the literature that will apply to all Eddington ratios. So let's now talk about some cosmological implications. Here's the equilibrium spin if a black hole just keeps continuing to accrete at a fixed Eddington ratio for a very long time. And I've demarcated 3 different regimes. We have hot accretion for low Eddington rates, thin disk for most familiar sub-Eddington rates, and then super Eddington. And we find that the equilibrium spin, as you increase from the thin disk regime, decreases slowly. And it's already at 0.8 when the Eddington ratio is 1, and declines very slowly down to 0. At some point, when you transition to a low enough Eddington rate, the thin disk should transform into a hot accretion flow. This isn't studied very much. Right now we have a sharp transition, but it would be nice to smooth that out numerically in the future. And then here are some example evolutionary tracks. Suppose you have some initial conditions for mass and spin, and then specify Eddington ratio as a function of time. Then you can work out what the mass, spin, and jet power are going to be. On the left, we have scenarios where the Eddington ratio is simply constant. And while that's pretty trivial to work out for the mass, the spin is pretty interesting. With the Eddington ratio fixed at 0.01, something that's initially very highly spinning goes down to near 0, whereas if it's at 0.1, it spins up to near unity. As I mentioned before, Eddington ratio of 1 goes to about 0.8, and then 20 turns out as around 0.18 or so. Each of these is tuned to produce a 10 to the 9 solar mass black hole at the end, because I had in mind, in particular, these quasars that we observe in the very early universe, for which prolonged super Eddington accretion is most often invoked, as opposed to in other contexts. And then on the right, we have some scenarios where the accretion rate in physical units is pre-specified. What I find most interesting is this red curve, which is following this particular power law shown here. It's meant to crudely represent, on average, the whole life of a black hole like M87, and it crosses all 3 regimes. in the early universe, it's highly super Eddington, spin is small, but then as it grows in mass, the Eddington ratio decreases, and then it's in the thin disk regime, evolving upwards, until it crosses back into hot accretion, where it starts to spin down, but it doesn't make it to the equilibrium spin because it simply runs out of fuel and runs out of time. So in conclusion, in mad accretion flows, electromagnetic jets produce efficient feedback and spin down. We've devised new formulae that people can use in the simulations. In future work, it would be nice to explore additional axes, metallicity, and mass, smoothing out that transition at low Eddington rates, and placing these in a cosmological framework. And if you're interested, you can download the paper online. It even includes a helpful Python script that has these recipes encoded. So thank you, and hope to take questions.
Thank you, Angelo. You focused on supermassive black holes, but then we also know stellar mass black holes, and in those, when they are made, obviously the conditions are quite different. Neutrino cooling is important. Do you expect to have similar trends, or would it be very different? Your formula will not apply.
I do not know how neutrino cooling would change this.
Well, Mesh knows, because he wrote.
Okay. there is a paper very recently in the literature, Gottlieb et al., I think it's 2022 or 23. They apply these formulae, or similar formulae, to these collapsar black holes, and the assumption here is that the mad accretion state, as you go to extremely large Eddington ratios, will be similar to that where the Eddington ratio is very small. Under those assumptions, you end up with similarly very small final or natal spins for these black holes.
Which can be tested by lab.
Yeah.
Okay, any other comments? If not, let's thank all our speakers today.